Hey guys, today we're going to do some review for Chapter 10, Work and Energy, and I'm going to walk you through a conservation of energy problem that involves rotation and kinetic energy both. And then we're going to finish up with combining some equations into a single expression because that's something we're practicing this term. Anyway, so this is the problem that we're going to start with here. We have a 40 kilogram solid rolling disc. It's rolling at 10 meters per second toward this slope, and it's going to roll up the slope without slipping until it stops. And we want to know how high it'll go. It's 40 centimeters in diameter. As I said, 40 kilograms solid rolling disc. Now, I can't do it on this smartboard thing, so we're going to switch over to the clipboard. And yes, there it is. Okay, very good. And so let's put myself down here. That'll be good. All right, so same thing, 40 kilogram solid rolling disc, 40 centimeters diameter, rolling at 10 meters per second, and it's going to go up here until it stops. Now, it is conservation of energy. So what we need to do is figure out the total energy in the initial state and the total energy in the final state. So initially, it is moving, so it has normal kinetic energy. So it's going to have that, some of that here, kinetic energy. And then it's also spinning because it's rolling, it's rotating, so it has some kinetic energy by virtue of rotation. So that's going to be kinetic energy of rotation. And that's the total energy that it has at the start. And then when it gets to the slope and rolls up, it's going to roll up as high as it can go. Since it's not slipping, it's going to stop rolling, stop turning when it gets to the highest point, and then it will all be gravitational potential energy. So these are going to add up to the, the U sub G, gravitational potential energy that it has up at the top. So now we're going to expand these terms out a little bit and apply specific equations to them, and then we'll work from there. So the straight line kinetic energy is 1/2 mv squared. Rotational kinetic energy is 1/2 I omega squared. And that's all going to add up to gravitational potential energy, which is mgy. Now we have a little bit more to do in here as well. So we have to figure out what the rotational inertia of this disk is. And we also want to be able to express the rotational speed in such a way that we can reduce our variables a little bit. So first off, the rotational inertia, if we look on our gouge sheet on page 210, we have a solid cylinder. Moment of inertia or rotational inertia is 1/2 mr squared. So that's what we're going to go for the I. So this is going to be 1/2 mr squared. Now, to simplify the omega, the technique we're going to use is we're going to remember our initial rotational equation, which lets us translate from straight line motion to rotational motion. So V equals omega R. So we can simplify this one as omega equals V over R. We've rearranged this basic equation. And then we can substitute in the V over R for this omega. So that comes down to be times V over R, and that quantity is squared. Because V over R is omega, that's omega, the whole thing has to be squared. We have to be very careful here that we don't forget about this initial 1/2. So we're going to bring that down too. So we get 1/2, that's the 1/2, times I, which is 1/2 mr squared, that's that one, times omega squared, which is V over R quantity squared. We don't have to do anything so fancy to the 1/2 mv squared. So I'm going to put this over here, mv squared, just so we have it all in one line, right? And that is going to equal to mgy. Excellent. So now we can start plugging in numbers because we should be able to work from here. So this is going to translate to 1/2, the mass is 40 kilograms, times 40, times v squared. The speed is 10 meters per second, so that's going to be 10 squared. That takes care of our straight line kinetic energy. Then we have 1/2 times 1/2 is going to be 1/4. The mass is 40 kilograms. Now, the radius of this thing is going to be 20 centimeters because it's 40 centimeters diameter. So that's 20 centimeters radius, which is going to be 0.2 meters. And that has to be quantity squared times the speed, which is 10, over the radius, which again is 0.2 meters. And that whole quantity has to be squared. And then that's going to be equal to the potential energy at the top, which is going to be 40, is the mass, times g, which is 9.8 meters per second squared, times y, which is what we want to find, y being the vertical distance. So then it's a matter of number crunching and solving for y. But I want to pause here and show that this is a conservation of energy problem. So what we've done is we've taken an inventory of all of the types of energy in the initial state and set it equal to the energy in the final state. And then from there, it's translating it into equations and teasing it out and doing all the stuff. So let's now do some calculations. We'll clear that up, and we get, well, we can do this in our head. 40 divided by 2 is 20, times 100 is going to be 2,000 joules. 2,000 joules for the straight line kinetic energy. This one we probably can't do in our head. So let's start over with this one here just to keep from getting too lost. So we're going to do 10 divided by 0.2, that's 50. That whole thing has to be squared. So that's 2,500. We're going to multiply that by 0.2 squared. And then we're going to multiply that by 40. And we're going to divide that by 4. So this term turns out to be 1,000 joules. Total of 3,000 joules. And this is going to be equal to 40 times 9.8. So 392 times y. Yeah, we'll set that equal to 3,000 joules equals 392y. So we can divide the 392 into the 3,000 times 3,000, and we get 7.65. 7.65 meters is equal to the height. And that's our answer. Ain't that grand? Okay, now we're going to take this one step further. Well, yeah, we're going to take this one step further. We want to figure out now, let's go back to the other one here. Go back to the smartboard. There we go. We want to change it up a little tiny bit. So now we're going to kind of do it backwards. And we're going to say we're going to take a similar disc. It's going to be a solid disc. And it's starting at the top of the hill. And we're going to roll it down. And we want to know how fast it's going if we're given the, if it rolls without slipping, if we're given its mass and its radius and how high it is. We want to figure out its speed v. Okay? So let's see. Yeah, let's go back to the clipboard here again and see if we can do all that. And I'm going to move myself over to this side. All right, so what we're going to use is basically the same expression because all of this is still true. The kinetic energy, linear kinetic energy at the bottom when it's rolling away, plus its spinny kinetic energy has to be equal to the potential energy that it had at the start. So it comes out to be the same expression. We can simplify it down. Now, again, we have to tease it out into all of these other terms. This is our next step, but then we'll take it from here. So let's see. Let's take it out this way. Now, rather than plugging in numbers, we're going to treat it purely as variables because this is one of those problems where they want us to keep it in general, only in terms of variables and not plug any numbers into it. So the 1/2 mv squared is not going to change. There's really no complications here. So let's keep that as it is. 1/2 mv squared. Now this is the rotational kinetic energy term. This one can boil down a little bit. So I'm going to simplify a little bit. So 1/2 times 1/2 is 1/4. We still have mr squared, so we'll keep that as it is. Mr squared. That's from the rotational inertia term. And now this v over r quantity squared, I'm going to make that v squared over r squared. All right, so I took v over r quantity squared. That becomes v squared over r squared. And then we're going to set that equal to mgy. Now, this can simplify a little bit because we have an r squared in the numerator and an r squared in the denominator. So those are going to go away. And if we also see we have a mass in the first term for linear kinetic energy, it's the same mass for the rotational kinetic energy, and it's the same mass that we're lifting up to the top of the hill. So, and that's in every term, so the masses will also drop out. And interestingly, this leaves us with 1/2 v squared and 1/4 v squared. We just that's how this problem, it happens to boil down quite a bit. They won't always do this, but this one does. So let's consolidate here again. We have 1/2 v squared plus 1/4 v squared is equal to gy. Now our task is to solve this for the speed. Remember, we in this one we're starting with the ball, the disc up at the top, and it's rolling down, and we want to know the speed at the bottom. So we're going to solve this for v. So this is going to be, when we consolidate it further, we get 1/2 v squared plus 1/4 v squared is 3/4 v squared equals gy. So we can move this over to the other side. So that's going to be times 4/3 times 4/3. Those are going to go away. So we get v is equal to 4 gy over 3, 4/3 gy. This was originally squared, so we have to take the square root of that. And there we are. Comes out to be v equals the square root of 4 gy over 3. Wasn't that fun? But it was kind of interesting in the sense that this huge ugly thing that we started with wound up boiling down quite a bit. Also notice that the mass does not matter and the radius does not matter, which is kind of surprising. But it turns out that any solid rolling disk will behave the same way, and it will have the same speed as it rolls down from the same height. And this is not entirely surprising, because if we drop any ball from a certain height, it will be going the same speed when it hits the ground. It doesn't matter the mass of the ball. All objects fall at the same rate. And it turns out the same sort of thing is kind of true for the shape of objects, or the composition of objects. All solid disks will behave the same way. All hollow cylinders will behave the same way. All solid or hollow spheres will behave the same as all other solid or hollow spheres. So a lot of this stuff does boil down, and it does simplify quite a bit. Anyway, hope that was helpful and informative. Yeah, you can go back and pause this and see if you can work it out on your own. That's probably good practice. I will obviously have a problem on this test coming up where you'll need to simplify some situation like this into a single expression. I won't use this exact one, but it will be kind of similar. And this will hopefully be able to get you started on it so you won't be just caught flat-footed with it. Anyway, thank you for your time, and we will see you next time.